Okay. Thank you, Ray. Thank you, everybody, for inviting me and talk about the wireless research that we have been doing here in Albany and how we can use Cosmos Testbed for improving the research that we have been doing. So first part of my talk, I will talk about one of my ongoing work, which is about learning from peers at the wireless edge. And this is one of the applications that we think that we will be benefited if we implement this in the Cosmos testbed. And this work has been done by 2 of my students. And in the second part, I will talk a little bit about what are the different challenges in working in a testbed and so far. So what we believe is the future is the fluid, the spectrum will be a fluid spectrum where we can see that there will be multiple technologies working together, multiple heterogeneous nodes working together, and it could be not just a few megahertz of frequency, but it could be multiple gigabits of frequency that is available for the nodes to transmit. Now, our goal here is to utilize the spectrum as much as possible, very similar to DARPA Spectrum 2 challenge, but not necessarily to push the data as much as possible, but to predict when the spectrum will be available and utilize that efficiently. So why can't we use Wi-Fi? We have seen Wi-Fi being used for many applications, and we use Wi-Fi for all of our applications, most of our applications today. It's most used wireless connectivity. The reason for not using Wi-Fi as is if we move Wi-Fi and in a dense network and we end up having multiple collisions, interference, we get a lot of space and bandwidth that remains unutilized or underutilized because of collision and back off. So that's why we would like to predict very accurately in microsecond order whether the spectrum will be available or not. So our assumption is that we should be able to multiplex not only in time and frequency, but also space. And there will be constraint devices in the network who won't be able to sense as efficiently and learn any of the parameters that we would like them to learn. And we should be able to help those devices use the spectrum efficiently. There has been many work which utilizes the operators. So federated learning has been already there, which can get the data, can get the models from different nodes where the base station can operate. And we don't want the base station because oftentimes the operators do not like to talk to each other or do not want to share their model of spectrum sensing and learning with each other. So that is where we would like to differ and move away from a federated learning approach where the parameters are captured by the centralized base stations. So what we are proposing here is a completely decentralized approach where we would like to learn from the peers. This is the traditional federated learning approach where the mobile nodes learn the parameters that we want them to learn. In our case, it is the channel availability or sensing data. And it learns, it trains its local model, then it shares the model parameters with the parameter server. That parameter server can be the base station. Most of the time it is base station because it needs to compute, gather data. And finally, model aggregation happens in the parameter server that generates the global model. And then that global model is shipped to all the mobile nodes. That again gets retrained. Now, there are pros and cons in this technique. So pros are, it maintains data privacy, so no one has to share what they're sensing or their own data. It can only inform the parameters of the model or the learned model. It generates a global view, and it creates a much complete model by aggregating all the information from different areas of the network. Also, it reduces computation overhead at the edge. On the other hand, some of the cons are that the global view might not be necessary. So for example, if I'm at home, do I really need to know how, or do my model really need to predict how the channel will change or how the spectrum will behave in a dense city network? Probably not. And in that case, if we keep the local information and local models local, then we are saving in terms of our model size. And that's where we move on, where we are trying to sense the channel. In each step, each mobile node senses the channel. Then it trains the local model on the sense data, and then broadcasts this local model parameters to all the neighbors or all the peers. Now, in each peer, when they receive this model parameters, they can calculate and aggregate and create the global model. The global truly is not global for the whole network. The global means that global here for just that particular node. So that node aggregates all of that and creates its own model. So this is going on into a little bit in depth, where each one of them, theta 1 to theta m, are different model parameters that are already learned by the sense data. And I will go into the details of how we are sensing what we are sensing. And once they reach a node here, we can aggregate all the model parameters based on sensing information and model that is being generated by its peers. And we can again train that. So it is an online training system that we can keep moving on in each node. So the way we have formulated the problem is we see that it is a training of a time series data, because either the channel is busy or the channel is available. And we need to know whether that information is available or that information can be predictable or not. So here, as we can see that each of the nodes are sensing the channel. So if we take a look at this, this becomes a time series data. The colored blocks are the portions where it has sensed the channel is busy. Now in this case, I would like to emphasize that some nodes may participate, some nodes may not participate in sensing. But in both the scenarios, if for example an IoT node is transmitting, its transmission will show up as a sensed data in one of these nodes. So each node will sense and train their local model. And based on that, the model will be computed in each of the different nodes. They can aggregate that data, parameters, not the data, and they can create their own model. This is again going into a bit of details where, as we can see that if there is a node which is Ni, if it sees something which has a channel traffic, which is lambda I, other nodes will also see the similar lambda I, will probably see similar lambda I if it is in one hop neighbor, and it can sense mostly all that Ni can sense. It will also sense more, which is from the two hop neighbor of Ni, and will gather that information as well. Now in each step, it can create and learn how these parameters are changing and how they will be in fraction of few microseconds. Now, what we are sensing is that whether the channel is busy for a delta period of time, and this delta is much smaller than packet length or packet duration. So if a packet duration is this long, I will have multiple ones here followed by multiple zeros, then again followed by multiple ones. And now once I do that, how it affects is the goal of this work is to figure out whether I can truly say that here in this case I have an empty slot where I should be able to transmit and utilize this instead of going into random backoff. And the result is stored as a binary time series. We used LSTM model where we looked at both short and long-term effects of these time series. And the data is mapped as 1 and 0 in the hot1 encoding form as a binary time series to the model. So this one actually shows that how the data model is aggregated. In this case, theta I is the local parameter, and the node is getting data from n neighbors. Now, in each case, we can adjust the weight of that neighbor's data or the parameter such that we can bring in different aspects to it. Right now, the WL, that's the weight, that is 1, which is linear average, but we are planning to have different aspects built into it. For example, a node has not trained for some period of time. So that node's model is quite old. So we don't need higher weightage for that. Or if it's a neighbor who is quite far away. So all of these can be built into this work. It also helps in solving the hidden terminal problem, because once we train and learn the model for both N1 moving to N2 and then from N2 to N3, we can predict not only how N2 will transmit, but also how N1 will transmit. So in that sense, we have seen that N3 can actually predict both N1's traffic as well as N2's traffic, because once it propagates 2 hops, once the model propagates 2 hops, it is able to understand how the data is being transmitted or how the spectrum is utilized. There is so all of the work that we have done here is a preliminary work, and it has been done using all simulation framework. So you can see that the probability for prediction accuracy is quite high in our both training set and testing set. So it goes up to 96% of accuracy. Also the loss, it goes quite low within very few epochs. We have also chosen multiple kinds of LSTM models, and I wouldn't go into the details of each of these because we are yet to see how that model size affects depending on the traffic model that we have in our data set. So another quick solution that I would like to show here is that one, we used a smaller LSTM model, which is the red line. Another one, we used a larger LSTM model, which is the blue line. And both reached very similar accuracy, but if you take a look at the epochs, the number of epochs required is quite large if it is a smaller one, a smaller neural network. On the other hand, if we truly look at the number of the actual time taken in seconds, they reach pretty much at the same time, because the time required for computation is much low for a lower or smaller size model. So all the previous work that I have shown so far, we have done only simulation, meaning that MATLAB generated data, move that to TensorFlow, then create the local model, push that, take that local model, push into aggregation, and then again push that data to another TensorFlow model. What we have not done and what we are currently working on is use this work and move this work to the testbed that we have locally in the university. We have a testbed which is Chronos, a cloud-based hybrid RF optical network over synchronous links. It is a cloud radio access network where you can see that the cloud is the FPGA GPU server, which we have over here. The edge nodes we have are Xilinx RF SoCs, and we have also built a custom RF optical front end, which will serve not only for the RF, but optical side of things. And all of this is an indoor setup where, yes, we have the capability to move around, but we do not have the capability right now to move beyond our labs or beyond the department because it's stretched out quite a lot, but it's still within the department. So that's where we think that Cosmos can help. We can predict the spectrum availability in city scale. We can use mobility. We can answer different questions regarding the hop counts, how to adjust weights, how the mobility affect the performance. And when I'm talking about mobility, it's like mobility in an Uber scenario or a taxi or how that affects. And what is the density required for this kind of sensing that I'm talking about? With that, I would move on to just a few more points in the challenges and expectations. So Cosmos, what Cosmos is, it's an opportunity for research. I am a systems researcher, and it's the paradise for systems researcher. It gives an end-to-end system. It's real time. We can do sub-6 gigahertz, millimeter wave, then the wired network side is built in. So it's truly a systems researcher's paradise, I would say. What still exists is there are a few challenges, and that's not related to Cosmos, but that's related to any testbed that we end up doing, whether it's an indoor testbed Chronos or it's outdoor, which is repeatability and reproducibility. So we have seen in many scenarios that I do my own research in my lab with my own setup, and then someone else does that and they don't get to see the same results or same gains as I am seeing in my results. So how can we ensure that we can do something that is repeatable and reproducible from day 1 to day 2? The main issue here is the channel changes, and that changes all the parameters in our system. What happens if we want to test new topology, if we want to add new base stations? What we want to do if we want to take it to a different city? What about the aerial channel in the city? So all of these are the questions that a testbed cannot answer. For example, scalability and dense deployment. In that case, an emulation can help us, and I would say that Colosseum has done a phenomenal job in virtualizing the channel, but it is also limited to the capabilities of the radio itself. So if I suddenly want to do millimeter wave scenarios or something that is 1 gigahertz of front end, I do not have that until I bring another radio to Colosseum. So that's where I think there is a chance for the community to help to come up with virtualizing the radio as well, not just the channel, but virtualizing the radio. And this is where we can learn from Cosmos and Colosseum how to mingle these two worlds, how we can create a digital twin of the physical world. Not to discourage that we still need the test beds that we have on the left-hand side, but we would like to see how we can change and learn from the test beds, model the front ends, and then virtualize in the data center. So that's where I think the wireless research would actually get benefited when we can have true frequency agile systems. We can have very high performance computing based on FPGAs. We can do efficient partitioning, making some nodes to be extremely small, some nodes more capable. So we can do all of these once we start virtualizing the radio. And that requires the expertise of high performance scientific computing world, as well as the analog devices world, to make sure that we can do this. And the last slide that I have is the community needs. I think at this point in time, we are sure that the community wants a benchmark. So all other research community has different benchmarking suites. And we as wireless community also need something like other domains. And lastly, we can have repeatability and reproducibility, but unless and until we make the code and data set available, it becomes very difficult to repeat and reproduce the work that has been done in Cosmos and other power platforms. And with that, I would like to thank you and take questions.
Okay, thank you, Dola. The inputs were very useful. So let's look at what questions we have on. Can you look at them yourself?
Yes. So the first one is per site. So
I believe that's the old one. That's for the
okay.
from all the stuff. Yeah. The next one is the one for you, I believe.
So regarding the Wi-Fi and cellular comment, is the users access in latest Wi-Fi technologies like .11 ACAX based on CSMA style contention based models, or they implement OFDMA style access control borrowed from cellular? So the part that we have implemented so far, we are still not actually transmitting. We are looking at when they are available, when the channel is available in different channels. So we have multiple channels, multiple space, and we are looking at whether we can predict whether it will be available or not based on OFDMA style model, I would say, because our channels are also like OFDMA kind of channels where multiple access can happen at the same time.
There is one more question on the panelist, on the chat, panelist chat.
Great talk. Thank you, Saptarshi. Quick question. What will be the latency overhead of such federated learning based on channel availability prediction? And that's a very good question, because what we have tested is on very simple simulated data. We haven't seen how it can scale with really large set of data, and the latency overhead per node, I would say right now is 120 seconds, but that can change depending on if we can throw in more GPUs in there. We haven't done much of that yet, so that is another possibility that we can utilize.